Well, three, two, one. Welcome to the PBE Podcast, first episode on hydrogen for the SPWLA Media Hub. I'm Troy Tittlemier, host of the PBE Podcast, co-founder of MagmaChem Research Institute, focused on new energy frontiers in oil and gas, critical metals, geothermal, geologic hydrogen, which is what we're talking about today. This series is about cutting through the noise on hydrogen with subsurface-driven, referenced conversations. These conversations are being documented for the SPWLA special interest group called ASET, Alternative Subsurface Energy Transition, which is now a great time to say thank you to the board of volunteers who keep these organizations thriving. So the ASET board members is the chair, Gerald Tischler, vice chair, Femi Onita, secretary, Robert Laranga, VP of seminars, Kelly Scoos, VP Geomechanics, Franz Mulders, VP Permitting, Katie Larson, and VP of Publications, Tom Bradley. We're talking directly to the people running projects and building data sets and translating that language into upstream and midstream operators, investors, technologists, something they can actually use is what our goal is. If you're trying to make sense of natural hydrogen, stimulated hydrogen, and where existing oil field skills fit into these new lanes, then you're at the right place. Today, I'm joined by Aaron Mattson, who not only works in these hydrogen exploration lanes we're talking about, but is also actively involved in defining them. In this session, we're going to hit three kind of main things: the basics of hydrogen for subsurface folks, and the two lanes exploring for natural accumulations versus engineering the subsurface for stimulated hydrogen. And finally, where operators and investors can realistically plug into this industry. Aaron, please introduce yourself.
Yeah, no, thanks, Troy, for putting this together. So my name's Aaron Mattson. I'm the founder of Mekic Consulting Group, as well as the CEO of Pahvant Resources, a multi-resource exploration company based out here in the Western U.S. I've been in natural hydrogen since about 2021, more focused on consulting in it since 2023 and 2024. We like to say that we're the first natural hydrogen consulting company here in the United States, and I think possibly globally, that was exclusively working natural hydrogen from the get-go, more with a focus on the industry, business, and economic applications, as well as the geology. It takes all parts to move this sector forward. So,
wow, man, that's incredible. We're talking about the exploration of hydrogen, the most abundant, fundamental thing in natural, Earth's processes is hydrogen. And now here we are in the 2020s talking about, exploring for accumulations of that, this element. So it's fascinating, and its role in all these other things that we do. Certainly oil and gas. Hydrogen has a major role in how liquid oil is made on planet Earth. And we're just technically starting to really dig into these things. Let's rock it back. Let's talk about kind of a level set. When you say geologic hydrogen, what are we actually talking about, and how does it sit next to things like the blue and green and these different colors of hydrogen that people already know?
right. So you can think of, I like to also call it natural hydrogen. I think geologic hydrogen is the accepted term, but natural is also an aspect of it. So when you talk about blue hydrogen, green hydrogen, what you're talking about is manufactured hydrogen. Even gray hydrogen is manufactured. So with green hydrogen, you're using electrolysis and usually renewables. Well, I think in all cases, renewables to generate hydrogen via electrolysis. You have blue hydrogen where you're using SMR, steam methane reforming, to crack your methane and essentially separate your hydrogen. But then you're taking the CO2 and you're injecting it back into the reservoir. So there's a carbon capture component to it. And then there's gray hydrogen where you don't do that. So when we talk about geologic hydrogen, we're talking about naturally occurring hydrogen in the subsurface that you're trying to identify in the subsurface and extract in its raw form.
Got it. And from your vantage point, who is active roughly? How many companies are chasing this accumulation of hydrogen versus manufacturing it or stimulating natural processes to make hydrogen?
Right. So last week or this week, as it changes. Um, there's over 100 exploration companies globally working on this right now. So within US and Canada, I'd say the majority of those companies are based here, but Australia also has a very strong exploration
Hmm.
grouping over there. So the main continents was happening on is North America and Australia primarily, although there is exploration also going on in Asia and Africa and Europe. But there's
Wow.
quite a few companies looking at this. Off the top of my head, I think there's somewhere around eight or more stimulated hydrogen projects versus geologic hydrogen. Primarily, it's geologic hydrogen exploration companies, but some of those companies are also looking at stimulated as well. So,
Hmm.
I think you're seeing more and more of that crossover from the geologic hydrogen companies also looking at stimulated.
Wow. And so from your perspective or vantage point, right, you're in it, you just explain that you're like the frontiers, right? You're part of the frontiering of this industry. And from your perspective, what's the difference of a company that's exploring for natural accumulations? What are some fundamental differences between that company and a company that's going out for just stimulating?
Right. So geologic exploration, you're looking for where it's naturally being generated. So there's a number of processes. The top three processes for natural generation is going to be serpentinization, um, which I know is
My
one of your
favorite.
favorites, right? Where you have a water rock interaction that is creating hydrogen. And we can get real technical on that, but there's certain types of rocks. Mafics, ultramafics, that have a certain type of iron content in it. And when the iron comes into contact with water at temperature, it causes a geochemical reaction that generates hydrogen. What we're
Extreme
looking for is,
temperatures and depths, pretty
yeah,
extreme environments, right? Okay.
pretty extreme environments. I mean, I think most of the models are looking for a temperature regime of 125 degrees Celsius or higher.
Wow.
It's been shown to be generated in banded iron formations around 90 degrees Celsius, but not at the degree that you see with like ophiolites or peridotite and other sorts of mineral regimes with hotter temperatures. So, that's the serpentinization is one of those processes that happens in the subsurface. You also have radiolysis, um, where you have radioactive rich rock, so uranium, thorium, at a deeper depth via that process. It can generate hydrogen, but in orders of magnitude less than serpentinization,
Oh,
but
wow.
over longer periods of time. So that's one method. And then there's the third method that's being looked at, which is deep mantle degassing, which is probably the one that we know the least about. There's a lot of theory out there on it, but it also increases the potential for generation in places outside of the normal serpentinization areas. So those are the top three. There's other processes as well. There's volcanic association. There's
Hmm.
mechanical generation that can happen along tectonic plate boundaries. Um, and one of my favorites is deserpentinization, which can happen at subduction zones. So there's a
Like,
lot of
yeah.
different processes, some more research than others. I'd say most of the primary exploration right now for geologic hydrogen is focusing on serpentinization. And the areas that they're focusing on that are where ultramafics intrusions have been pushed up closer to the surface where we
Have to
can
be, right?
access them,
Right.
where you have ophiolites that have been thrust up off the ocean floor onto what we'll call dry land in this case. Um, or in, I think most of the exploration is actually happening in mid-continental rifts. So the
Whoa.
like the MCR in Kansas and Iowa that extends all the way up into Minnesota and wraps all the way around Michigan was one of the first primary focus areas.
One of the
So you're
biggest
looking at
geologic wounds in North America, right? Like this
right.
thing
Any
is,
sort of deep earth processes that can push that iron rich rock into the shallow crust is a focus area. Mountain ranges are also an area too. There's a lot of exploration going on in the Pyrenees on the border between Spain and France. There's groups looking in
Wow.
Switzerland too. There's groups looking in yeah, see northern India along the
Wow.
Himalayas. So there's I could go on and on and on, but
Yeah.
that is the focus of the exploration. On the stimulated side, they're not looking for that natural heat gradient. They're trying to, I mean, in some cases they are looking for it, but they're not looking for the perfect combination of geology to naturally generate it. What they're doing is they're going in and they're looking for the best rock that can generate it. And ideally, in some cases, a geothermal gradient that also adds the heat so they don't have to. Although there are
Wow.
companies looking at trying to get around that. And they're drilling into the rock, fracking it or cracking it, injecting water into it, and then using that heat gradient to generate hydrogen via serpentinization. And I mean, we're still in the early days with that. There have been pilots. There was a major pilot done in Oman recently, with a lot of data coming off of that to look at,
Nice.
you know, what orders of magnitude of hydrogen are getting generated and what do we have to increase it. And that paper came out from Alexis Templeton's group. I think she's
That's
probably one of
amazing.
the top people spearheading some of the research out of this at the University of Colorado in Boulder.
I want to
So,
see the chemical reaction to that. I wonder if there's there a good paper that shows just kind of a chemical reaction breakdown of like, okay, you have a peridotite, you kind of know what your olivine to these other minerals are in the peridotite. You're going to crack this rock, you're going to inject water into it, and that's your formula, your chemical breakdown. You're going to have a product of that where hydrogen is being abundantly made, on the other side, that reactant, right? So I would love to see that. You got any references or anything that you can share with us?
yeah, I can send you something on the back end of the show. So,
Great.
yeah, I believe there's some pre-published content from Templeton's group out there on
Sweet.
the Oman project. There's a lot of other research you can find out there in various publications over the last 2 years. A lot of the work that's been done on it, though, is I'd say lab work. I think we definitely need more field demonstration research. Most of the lab work is done by taking the rock sample, grinding it up, putting it in a reactor, and then testing the process under pressure and temperature.
Wow.
But my opinion is that is that grinding rock into small facies and having the perfect conditions for it's not reflective of the natural environment. There's a lot of other processes that happen once you
Yeah.
generate the hydrogen and the mineralization that occurs. So I think we definitely need better lab experiments that are more reflective of the in situ conditions.
Yeah.
But there's a lot of really good research on reaction rates for different types of rocks. I mean, I think they've run it on dunite.
Okay.
That's that one's definitely a preferential with the amount of olivine that's in it. Peridotites and other sort of samples have been run through in the lab, and reaction rates have been generated. I mean, we know it's being generated.
Right.
That's really not in question.
That's right.
Um, I think more of it is the model for extracting it, and there's a lot of other processes that are occurring in the subsurface that we still have not been able to accurately model. Because just because you have hydrogen doesn't mean that it stays hydrogen. And I think that's one
Wow.
of the biggest challenges that we have with where we are right now on the research is there's a lot of things that can consume it.
Right. Yeah, it's the most
Turbulence.
reactive, like cat ion thing, right?
Yeah, and I mean you have other mineralization processes as it migrates, as it interacts with with the rock
Whoa.
surfaces. Even the process of serpentinization, it creates an expanding surface as it happens. So if you have in stimulated hydrogen, I think the challenge is not just generating hydrogen, it's getting the hydrogen to migrate out to where you want to extract it out of the ground. And as you generate this process, you are decreasing the density of the rock, which means that the rock is whatever cracks that you had are starting to close up as that process occurs.
Wow.
Um,
Wow.
on the other side, with geologic hydrogen, you're generating it deep, deep in the crust. it's migrating up through the sediments. And as it's migrating through the sediments, it wants to interact with everything. Hydrogen, if it's running into kerogen at certain temperature, certain pressure, there's an interaction there. I mean, one of the areas of interest that I have is what beyond just the focus on pure hydrogen, the knowledge that comes from knowing hydrogen's being generated and migrating in large quantities over geologic time is what happens when that hydrogen interacts in the subsurface. It's going to tell us a lot about mineralization. It's going to tell us a lot about hydrocarbons. It's going to tell us a lot about other processes where we've never included hydrogen as as part of the system within our crust.
Not a part, like a leader of the system, right? Like this thing's the lightest, it's the most volatile thing. Like, yeah, hydrogen is, dude, primary.
So that kind of gives you a little bit of the understanding is one, we're stimulating all the right variables and processes to get it going. And we can do that, trying to do that a little closer to the surface. The other ones, we're letting the earth do what it does and hoping it's generating enough that it can migrate in like a hydrocarbon can migrate into a trap where it can accumulate. And
so
one well shows that today.
It's interesting. It's fascinating that the hydrogen industry, hydrogen exploration to me has led to a very similar thing that's developed over the last 100 years in oil and gas. You can explore for fresh pockets, untapped parts of the earth that have a natural accumulation deposit of an oil reservoir. And then you can go into old places with new ideas and stimulate the rock in a way and enhance its oil recovery where it already had the big fall off of production, but you got the right technology and you're gonna increase that decline curve again, and you're gonna stimulate it. So from your perspective then, and to wrap up this segment real quick, what kind of workflows do you see really overlapping in the last 100 years of development for oil and gas geologists, geothermal, all these other industries, even mining? What overlapping technologies are you seeing being applied to hydrogen now?
Yeah, I'll start with mining because that's one that I think is starting to get more attention. I mean, a lot of the tools that are being used in mining are now being used for geologic hydrogen exploration. Mag and grav, and trying to understand how to identify where that rock exists in the subsurface. So, I mean, there's some pretty impressive inversion modeling that's been being done with mag and grav data. So, I mean, changes in the gravity and the density are a direct effect of serpentinization occurring. So if you can model that out, you can see where you're seeing rock being serpentinized or where it's not. Your magnetics are picking up on higher iron content intrusions as well. So even some of the survey data from the mining side and some of the modeling concepts for looking for where that process could have occurred or is occurring kind of start to play a bigger part in geologic hydrogen exploration versus the typical oil and gas tool set. On the oil and gas side, you're looking at traditional uses of seismic, trying to identify those structures that are going to have closure and are possible accumulation zones. Faults are your primary method of migration. So you got to understand all the different parts. Using the oil and gas model, I think, is pretty important for understanding not necessarily how it's generated. It's not in the typical kitchen that we use for oil and gas, but how it migrates and how it accumulates. All that tool set from oil and gas gets applied here. And a lot of the well logging tools become very important too for understanding where it's accumulating, where you're seeing higher hydrogen. I mean, every single exploration company out there is testing for helium and hydrogen when they drill a well. When they're doing their well logging. So
that's awesome. It's interesting. Hydrogen's getting more and more attention. And so, yeah, so that's it. There's some interesting overlap there. The production of this, it's mostly a gas, or are they fighting like fluids, like a brine coming out with these discoveries?
So you're touching on a kind of a hot button right now for a lot of the early exploration results. So there's a group out of France called FDE. They had the project up in Lorraine, and they were drilling into an let's put an aquifer with hydrogen. and with high hydrogen content. And so hydrogen, when it's under pressure, it dissolves quite readily in water. Um, and a lot of the exploration wells that have been drilled into aquifers, or in some cases it's brine, that carries a lot of hydrogen in it. So they're getting a lot of hydrogen, but they're getting hydrogen in water, which creates a challenge on the economic side for separation. There's also a limit to how much hydrogen can actually accumulate in your water. So the ideal situation is to find an accumulation that is not dissolved in water. But then water is oftentimes your drive for pressurizing the reservoir, but at the same time, it's dissolving in it. So a lot of the dynamics for how hydrogen interacts with water in this whole system, that's one of those areas that I think there's research continues to look at, and we're trying to better model, because you're going to get a higher accumulation if it's not, and the separation costs can be pretty high. But there's also companies working on technology that can maybe deal with that situation in situ. So
Nice.
water is, it carries hydrogen, but it also have hydrogen dissolve into it. So getting hydrogen out of the water is definitely a challenge. Our best bet is to go and try to find accumulations where we don't have that.
Wow, man. Interesting. Let's go with our final segment, kind of the takeaways, right? And really the operator side of things. So you'd be getting practical. If you're an operator in Texas, you got the subsurface experience, you have an appetite for experimentation, right? You're thinking there's got to be other ways to generate revenue here, not just oil and gas. I have the seismic, I have this land position. What are the first steps, do you think, or would you recommend for an operator in that situation to start thinking about for the development of this in the next couple of years?
Well, I think there's a lot of operators out there who have a strong understanding that hydrogen does exist and has existed, and they've seen it in their wells. A lot of the wells that we have focused on, or the exploration areas that we've focused on over the last couple of years, have been wells that were drilled for oil and gas. So, understanding, if you're not jumping straight into it, that there are other gases that come up with natural gas, or that come up on their own. Recognizing that and knowing when to identify that, there's a lot of tools that we have out here for identifying hydrogen. So I think the simple answer is knowing when you might have hydrogen and being able to identify it very quickly. If you drill a hydrogen well by accident, the value of that well is not, if it's not an oil well and you're pulling gases off of it, and you have a high hydrogen content, and not going to do anything with the methane that's coming out of it, there's a lot of commercial potential in those holes. A lot of hydrogen exploration companies would take a deep interest in it, and possibly be interested in
Farm in or something, yeah.
farming in, or coming out and taking over that well. So
Wow.
Just being aware of it, I think, is the first step, and aware of some of the tools that can identify it. And what you think might be a dry hole for hydrocarbons might actually be the next well for hydrogen extraction.
Wow.
So I think that's a big piece of it.
So say you got a bunch of horizontals laid out. You're fighting the decline curve. You drilled up what you feel like is your tier one. You go in with some money. You go, I'm going to drill some vertical infill wells across these horizontal positions and kind of see what happens. And then someone strikes hydrogen. What are they going to do with that in the middle of an oil field that's developed all this oil and gas? Are they going to convert that to electrical energy right there on site, or are you piping this off and trying to get someone to buy it and drive it away?
A lot has to do with the purity of the gas. So, I mean, if you're pulling something that's 95% hydrogen, here's the other thing too that you have to consider is, with hydrogen right now, I would say you're ideally hoping that there's a strong helium percent, or a pretty good helium show with it too. So helium is going to make a lot more money than the hydrogen will at this stage. We just do not have the infrastructure to easily move hydrogen around. Now you can take it off, separate it, compress it, and truck it out. If you're within 50 miles of an ammonia plant, I mean, there are options to sell the ammonia.
Okay.
if you're out in the middle of the Permian, your
Yeah.
options for offtake become a lot less. But I mean, it's something as simple as you can hook it up and possibly burn it and use that for electrical generation on site to power
Sure.
your other infrastructure. So
Yep. I got you. Okay. The biggest technical uncertainties, I think we touched on this a little bit, but let's just recage this final thing, this final thought. Deliverability over time, monitoring the environmental risks. What are the technical uncertainties right now from your perspective?
I think it depends on which one you're talking about. So geologic hydrogen has different uncertainties than stimulated does at this point. So we'll start with geologic hydrogen. So I think one of the challenges we have is in the exploration side of things. Knowing where to look and what tools to use, I think is where there's a lot of uncertainty. Some of the places that we thought would be the best turn out, in parts of Kansas and other wells that have been drilled were not successful. I still think Kansas has potential, but we've drilled a lot of wells there. I think there's close to 10 wells that have been drilled in Kansas at this point
Wow.
that we know of.
Yeah.
um, so I think one of them is better tools for identifying hydrogen before you actually start to drill. We drilled a lot of wells unsuccessfully, so the dry hole risk is pretty high right now. So I think there's a need for some new exploration tools to be able to de-risk the front end a little better.
Okay.
The second one is migration. So what's happening between accumulation and generation? That's we see a lot of hydrogen being generated or the potential, but we don't see it showing up anywhere. So that
Mm.
could be consequence of the trap. But I think microbial consumption, its contribution to mineralization, its interactions with other
Wow.
things in the subsoil cause an issue. So those are the two areas: is really having a strong understanding of what are the conditions for migration that can preserve it. So preservation during migration, I think, is one of the biggest challenges that we have to really understand. Stimulated side,
Preservation. Say that again.
uh,
Preservation during migration. Is that what you said?
yes.
Okay.
It's not a problem you have as with oil and gas as much, right? It's generated, it migrates, it accumulates. But hydrogen interacts with everything and wants to bond with everything. So you need those conditions where it can migrate very quickly and not interact with a lot of stuff. It needs to be blindfolded and it needs to be pushed to the reservoir. So
Right on.
you don't want it running freely through the subsurface interacting with everything.
Yeah.
So that's a challenge that you don't have in oil and gas. And the models for oil and gas are really not sufficient for that aspect of it. On the stimulated side, I mean, there's a lot of research going into this, but I think understanding how to expedite the generation of it, I think, is one of the biggest challenges, because there's a lot of other things that happen geochemically when you start this process. You're
Yeah, you were talking about
changing.
that.
So once the serpentinization process starts, there's other geochemical variables that you're also trying to control. It's the
Wow.
alkalinity of the water that you have down there. This has to be controlled as well. If the alkalinity changes too much, the generation can start to cause other geochemical
Wow.
processes. So it's a geochemical problem, is what it is, and you're trying to how do you control the variables to keep it right in that perfect spot where you can get
Wow.
that generation at levels that are commercial. And
Yeah.
they're looking at injecting different types of solution. So you're engineering the cocktail that you're
Mm-hmm.
injecting to optimize that. You're looking for how you can, artificially create the right interaction surfaces with the rock to the water. So fracturing, understanding the fracture networks and how to do that. A lot of it comes down to is you're looking real granular at where that
Yeah.
interaction is happening and how you can speed it up. So in the stimulated side, a lot of what they're working on is through heat, control of the solution, and monitoring it so you can control
Wow.
it.
Yeah.
Yeah, they're two very different challenges right now
Yeah.
on both different sides. There's a lot of research going into. I just got back from the Gordon Research conference over in Maine, and I mean there was over 100 researchers from all over the world there with their published work, and talking and
Nice.
discussing both stimulated and geologic hydrogen at, what are the current challenges that we have to overcome, where's the research going, and looking at ways to collaborate. I think collaboration between operators, between researchers, between exploration
Yeah.
companies, is there's a lot more collaboration that's needed. We haven't solved the problem yet. So
Yeah.
there's challenges to getting this to a commercial state right now.
Wow.
And that's going to require kind of everyone using their shared background, because it's not like oil and gas. There's there are so many disciplines, from geothermal people to expertise in geochemistry to expertise in petroleum engineering to geophysics. It crosses the gamut of every single discipline you can think of
Yeah.
in the geological sciences.
Wow. Man, fascinating. Thank you for taking the time to go through those questions. Let's open it up. We got Natasha and in the on the walls listening into all this. Let's shift into the questions for the audience. So, Natasha, please introduce yourself and what's your comment or question for today?
Hi.
Hi.
Hi, Aaron. And
Hey,
hi, Troy. Nice to meet you. We follow each other on the LinkedIn, so I do carefully watch your posts, and Troy, thank you really very much for organizing this, because this is a petrophysics community. So I'm glad you are Aaron, you are the guest today. So I am the founder and principal scientist of the Petrodexia, and I'm also coming from the oil and gas. I was mostly in the R&D, working on the solutions for the petrophysics community for more than 25 years. And Petrodexia is working on a stimulated hydrogen. And
oh
so,
great.
so we basically, my experience was heavily related to the tight gas and unconventional shale. And so basically what I like to say is that, we knew about the source, but we actually engineered the, the oil and gas from the shale.
Right.
So that's basically the mindset that we're going into that direction. We're not looking for, our stimulation technology. We do have a couple of innovations. We unfortunately cannot talk a little more than what just I'm gonna hint to it a little bit over here. We're not looking into heating the rock. We're typically looking for the lower temperatures, a little bit different processes that they are, a little different mineral framework. So that's basically the direction we're going into, and we're also very interested, a lot of mining sites that they are offering a number of good things, like the data, as you know. And so also the technologies that the mining industry has. So there is a lot of, let's say, when you go to the checkbox, what you have and what you need to engineer after that. So it does really
Hmm.
tick a lot of boxes, to go in this direction. And also based on the experience, what happened with the unconventional shale. So, and a lot of things that you mentioned, what are the challenges? The challenges are the accumulation, the migration, how to bring that to the surface, and so on. So if we can, prove something like that in a shallow subsurface and then answer some of those questions, then we can possibly go deeper. So that's why I think that value of going into that direction is to actually answer some of those questions. It might be valuable, for the future and for the then basically continuing to explore for the accumulations, but to answer those questions through the stimulation processes. So that's where we are, and I don't have a questions. I mean, Aaron touched base on a lot of challenges. There is a lot of challenges, and I do completely agree the collaboration. And I do see actually hydrogen kind of the bridge in between the oil and gas and the mining industry, because that's where it's going to be, to use the expertise of us, like Troy Petrophysics community. We do know the
Yeah.
subject really well, so. and to use that expertise, to use the technologies and lessons learned through these unconventional efforts that we had in oil and gas industry, and then with the technologies, to combine that with the technologies and the data that exists already with at the mining sites, because they do have frameworks that we're looking for. So
Interesting. I got a question for you because your background, unconventional, and how you were able to be a part of cracking this rock and getting a commercial amount of oil and gas out of it. It's similar to what Aaron was talking about, how you're going into a rock that maybe needs stimulated and you got to have the right alkalinity, you got to have the right water chemistry that's going into that rock and creating this reaction. A fun fact that I covered, or I didn't cover it, but I read it on LinkedIn and I said it in a previous podcast. Someone was showing the relationship that the amount of water that goes into an unconventional horizontal well that fracks the well. So say it's 1 million barrels of water goes into the well to get fracked. The amount of water that the engineers report that doesn't come back. So 40% of the 1 million barrels is lost in the fracking process, equals about the amount of the estimated ultimate recovery for that well. Have you heard this?
no, I haven't. No, I haven't.
So
Yeah.
you frack a well with 1 million barrels, you start getting all that water back, your chlorides drop off, and you go, man, we didn't get 40% of that frack back. You can estimate off that result that well should make you about 400,000 barrels.
Yeah. So I do, to be honest, the model that we have, it will not include initially the fracking. So this is going to be without the fracking. But of course, it's going to use the water. So we have to stimulate with something, right? But there are, Aaron touched on that topic, that there are a couple of different methods, for stimulating the hydrogen. There are some, electrical methods for the microfracking and so on, but we're not going to focus on the fracking. Basically, what is needed right now is to demonstrate how all these challenges are going to respond to what we're going to do to the subsurface. So once that it's demonstrated and validated, we can actually bring that hydrogen at the surface. So the roads are open, and then it comes the next stage about how we can scale it, who are the off takers, and everything else. But I think that's the number one. What we need to do, and it will contribute to answer all the some of the questions. Of course, like for the shale, how long it took us. But when you think, Evan mentioned that that there is a lot of lab work that it's been done. Yes, there is a lot of lab work that it's been done. But what we were doing in a lab, we were actually stimulating, right? We were pushing the water through that rock, and we were looking at the oxidation process, and we were looking at that hydrogen yield. Now, what we need to try to do that, it's the same thing, but the subsurface. So let's stimulate a lot. Let's take that lab into the subsurface and then do the same thing what we did in the lab. And so inject that water and then basically create the real world lab.
Nice.
And the one thing is, I've seen in some papers that what is in the lab, it's not exactly representative of what is, probably we need to have like a 10,000 fold. So a lot of people are saying, well, that's just a small amount of hydrogen that is generated in the lab. But however, you're just taking, I don't know, a couple of tens of grams of rock, and then you create a powder of that rock, and it's not really realistic. The subsurface. There are some papers that they were trying with the chips, with the slabs, and so on, and so they were actually analyzing, what if you have a different geometry of your sample, what would be the that hydrogen yield. But we basically need to create that lab subsurface because we have a different volume, different exposure.
Sure.
And so on. And that's exactly the same thing happened with the shale. In a lab, we did understand all the maturities, all the, everything what we needed to know. But then when we went into the field, the things were different. And then
Wow.
in that engineering part, it says, okay, so what kind of a water, what kind of a pressures, what kind of a sand, how are we going to keep those structures open, and so on and so on. So, but it is of course different mineral framework. We needed to keep that shale open,
That's right.
and the oil flowing. But
That's
for
right.
the environment, we probably need to try without that, and then see how far we're going to go. So.
Very nice. Aaron, you got any follow-ups before we land the plane?
No, I agree with her on pretty much everything she said. We do need to move off of grinding powder in the lab and using that as our base case, and moving on to more sophisticated bench testing and in situ lab to
That's
really
awesome.
understand it, to be able to move it forward. And I know that the closest group to it right now is VIMA. They've got a project up in Quebec.
Yes.
So I'm hoping that I don't represent anybody, so I'm hoping that they have something that can help continue to raise the investment to drive the research forward in this area. And it's going to take a lot of engineering, a lot of geochemistry. One of the things I'll add, though, that I think is going to be needed for us to really do this is better downhole monitoring systems.
Yes.
Being able to get measurement or monitoring into that lab environment in the subsurface and see what's happening, or understand what's happening in the geochemistry. Even changes in temperature inside of the environment is going to be useful data. So that's one of those areas where I'm kind of excited to see what applications people come up with, or what vendors start to come out with solutions to assist in that, because we really need to understand what's happening, not just see the end product, but to be able to see what's happening at every stage of it, so we know how to control it better.
That's interesting. I mean, the probe of the oil and gas industry is just steel tubing, and maybe a packer. Just get it down there, get it close to the purse, and let that reservoir come and see you and separate it at surface. And what you're saying is we need to get a much more sophisticated probe in our production string and how we're going to produce these things, whether it's the injection string or the production string. These things need to be wired with fiber optics and pressure gauges and all these, everything we can get down there to understand what's coming out and what's going in, how's it changing, doing the mass balances, right? You need some serious chemistry. Is that what you're getting at?
Yep.
Wow.
I do think, absolutely, I agree, Aaron. I do also think that in that process, not only maybe downhole tools, but at the same time, some surface monitoring as well. And so that surface monitoring and plus the downhole, during that demonstration, until we figure out what exactly the technologies need to go forward. And that's what also shale did. In the beginning, we didn't have all these technologies. And then we developed in time, we developed more and more, not just the technologies, but also, the approaches, the workflows, and so on. So, and it wasn't just one company, everyone was contributing from the different angle. Something to the industry. And that's where I'm also saying, all these companies that they're now working, including us, and in the stimulated and in accumulations, it is a learning process. And every single outcome from each one of them is going to be really valuable, because we're talking about, big industry, right?
Yeah.
That's a collaboration is going to be the key.
Yeah. All right, Stan, you are the co-founder, leader of the MagmaChem Research Institute. By all means, I do what I can to help and encourage you to continue the research and your take on scientific discoveries. What'd you get from the show? Do you have any comment or a question in particular that we can dive into?
Okay, and my first question to those guys is, have they read the Lewin papers?
Good
because
question.
he's all over this. And he looked at what hydrogen was doing during all of his experiments. He monitored it.
Yeah. Now he did. I'm not wondering if have you seen him do any kind of experiment on a serpentine, on a peridotite?
No, but that was funny, because after I talked to him a number of times and we got to know each other, finally said, listen, I want to I want to check you guys out. And so I want you to get me some good serpentine, and I'm going to run my experimental protocol on it.
Wow.
But we never got quite that far because he retired. The lab's kind of been mothballed. I don't know what its status is. I know he's still around.
Yeah.
And we would definitely like to get him back in the loop. And I don't know if these guys, there's a lot of stuff in his papers that could be taken advantage of from that discussion that I was just listening to. So the other thing that is important, several just thought experiments. Number one, what happens when you have a gas accumulation? Is it stratified? So in other words, we all know there are different kinds of gases, and hydrogen and helium are the lightest one, with hydrogen obviously being the lightest one. Is there a hydrogen cap on top of your conventional gas reservoir that nobody's been looking at, or it just sort of escapes?
Right.
Because they're
it comes off
focusing
as
on
gas.
what's underneath it.
Huh. Yeah, somebody's got to know some answers to that. You got all this gas coming out of the well. They're
Yeah, but I
sampling
haven't
it.
heard that in any of the discussions that I've been listening to so far.
Interesting. Yeah.
And the other thing is, that we were doing a little bit earlier, is that when you're acoustically playing around with this stuff and you're changing the coordination states of water molecules, you're also making hydrogen as a proton. And you're and you're doing it in the context of brine. And the question I have is, if there's not enough kerogen around, are you making excess protonation that is dissolved in the brine that was getting at what was being talked about as hydrogen-rich water?
Yeah. Wow. Yep, that's right. I mean, it's got, yeah.
And that's a great hydrogen carrier. It can carry it, and it's actually kind of a natural trap, because as long as you can keep it dissolved in the water and not depressurize out of the water.
Yeah.
So if you could somehow capture a hydrogen-rich brine and not depressurize it, that would be another possibility.
Interesting.
And finally, there's another possibility that one of the things that I did not hear was the concept of hydrothermal hydrogen.
Huh.
Rather than natural hydrogen. And most hydrogen is really a hydrothermal process. So I think natural hydrogen is a bit of a misnomer.
Okay.
So in that context, there's a lot of ways to make hydrogen other than just serpentinization. And I noticed there was almost an over-reliance on iron. But once you're making a generic mineral deposit, it doesn't necessarily have to be sourced in a serpentine. The carrier can be something like H2S. So if you have sulfur around, you can get a lot of sulfur hydrogen sulfide as a carrier, dissolved in a brine. Now that's very reactive, and if you've got metal complexes like copper chlorides running around, and you react that with hydrogen sulfide, you create a copper sulfide plus hydrogen, and that was going on in the Kupferschiefer all the time.
Whoa.
So there's a lot of places where sulfides might be happening associated with black smokers out in the Gulf of California, for example.
So some of these black smokers could be just hydrogen vents.
Hydrogen generators, yeah.
Wow, that's
And again, they're
fascinating.
typically not assaying for it.
Well, who's even going out and paying the $1 billion to go even find one and then assaying the thing? Like it's got to be
Well, no,
super rare good.
I mean, they found these black smokers. That was pure research,
Sure, yeah,
like at
pure
31 degrees
research,
north.
not to be not to be considered as a production target, right? Not to be considered as like an
No, just
energy
to see what was
source.
there.
Yeah. So now
They didn't
you gotta
even know
build
these
these.
things were there. They didn't even know they were there, let alone whether there was a hydrogen anomaly associated with it. But if you're making and precipitating sulfides, and it can be iron sulfides too, but it can be copper, zinc. Zinc's probably the most common one. You're making hydrogen because you are precipitating those things from a hydrogen sulfide rich hot brine.
Wow.
And that doesn't necessarily have any, you can do that in the context of serpentinization because you can have serpentine source H2S, which would be what the Kupferschiefer was. But you can also have just generic H2S, hydrogen sulfide, being generated in the context of porphyry copper mineralization, and you're going to generate hydrogen.
Wow.
But the problem is, if you do that, the oxidation state's a real important parameter there, because if it's too oxidized, you're going to react it to things like water just immediately. But if you can keep it reduced, then you're going to tend to preserve hydrogen.
Wow. So what? Okay, a Lewin paper. Obviously, I can upload that one as a reference you'd like to see added to this discussion.
Oh yeah.
What is this copper oxide angle paper that I need to go find? What is this? This seems very interesting.
Kupferschiefer.
The Kupferschiefer 2022 publication.
Yeah, I have a couple cartoons in there that are stolen from some of the Germans.
All right, I'm gonna upload both
I
of
love
those.
doing that. And you have them.
Yeah, I'm gonna upload the Intech paper and I'm gonna upload the
Yeah, there's two
Lewin.
of them, but I think it's the second Intech paper that has how you actually make oil out of this. But in the context of that, basically the oil generation process after you leave the serpentine kitchen is a hydrogen generator and also potentially a helium generator. Now, the Dinibakea thing, it seems that more alkaline magmatism may associate with helium in terms of possible
Wow.
commercial possibilities. Because
No
they're still
shit. So
generating a lot of helium at Dinibakea right now.
wow, and it has something to do with the deeper layers.
Yeah.
Interesting. So these nepheline super
Well, it's
alkalic,
actually the alkaline, probably the melanephelinitic layer that is those things are coming from. They're really coming from the deep.
is that Balcones fault section, or am I in the wrong in the
No,
wrong?
you have the right alkalinities down there in terms of the layered mantle model. That's down there, and
Wow.
some of those magmas could be generating helium. Well, the
Right.
fact is you have helium in the Texas Panhandle.
Right. Yeah, no, major helium stuff going on up there. But down here, and the idea that they're tied to
Well,
these mafic
I wouldn't
intrusions.
necessarily overlook that.
So that's a fascinating look back, because a lot of these things, these sand
The thing is, a
deposits.
lot of these, they get all locked in on a specific chemistry, and then that's all they look at because they're
Right.
in production mode.
Right.
But I
Exactly.
think when you're teeing up field X, Y, or Z, you should be doing a complete chemical take on it because you might find things in there that you need to be looking at.
Wow. Wow. Interesting, Stan. Always bringing a great angle.
And that would be helium, and it would also be hydrogen. And again, I think those things tend to be so light, they're going to float and they might escape off the top of a typical gas reservoir.
Yeah, either through microfractures and things like that, you're
Yeah.
thinking? Yep.
Yeah, but depending on the reservoir's characteristics, you might be able to trap it. But the other thing is the brines might be able to carry it and trap it. A self-trap, because as long as you can keep them dissolved in something.
Pressurized.
Yeah. Yeah, it's like your champagne bottle. You can keep that CO2 in there until you pop the cork.
Yep. It makes a hell of a show. And it only lasts for 2
Oh,
minutes.
the interesting thing there is that when you pop the cork in a gas reservoir,
Does it pop?
just don't let it bleed off, because you may be bleeding off all your hydrogen and your helium. Just thought experiments.
I love that. Okay, well, let's land the plane here. We're obviously going after getting the data, getting into field applications and testing, doing the research needed. That's really what we're after in these shows and in these segments that we're putting together. We want to put the references, any slides that we shared, what we mentioned in this show is going to be available to the community so they can engage with it in new ways, access this information and your guys' experience and knowledge on this subject. That's what we're building here for the SPWLA, the ASET organization, the special interest group, right? We want this accessible. We want people to engage with it. Aaron, thank you so much for talking us through this. And if you know anybody who you think could be a good fit for this show in the future, please have them reach out. Let's get them on the show. Let's continue to talk about this subject, how we can learn from all these other industries applied to hydrogen and vice versa. What can we learn from the hydrogen industries that we can go and apply back to the older industries? So from the PBE podcast to everyone listening, Natasa, thank you for your comments and questions and being a listener. We will see you on the next one.
All right. Thank you.
Thank you.
And maybe see you in Poe next year at the SPWLA, right?
Let's go to Poe. All three of us are going to Poe. Let's do it.
Yes. All right. Thank you. Bye.
Thank you, guys. I like the matching Magma Chem LA Dodgers hat tire going on right now. All right, Stan. So you were saying the pre-alkaline volcanism, more of that classic igneous style process kicks on after the mud volcanism process.
Right.
In both.
And that's what you see in the mud volcanism in the Balcones. It predates the emplacement of the various volcanics, diapirs, flows, etc.
The muds are coming out right before ish. You have no.
Yeah,
what's
but
the
you
time?
don't know how it's pre, because nobody's ever dated one of them.
Millions of
The
years, you
dates are
think, or
always on
hundreds
the
of.
volcanics.
Right. So you get the muds adjacent to the volcanics, age date those, and you're saying that it could be pretty close in
Well,
age.
what we know about them is we're age dating them stratigraphically. For example, the Eagleford stuff.
Yes. These things punch through the Eagleford and then they kind of truncate or daylight it, if you will, up in like the Wilcox or Escondido, right?
No, they daylight several places.
Well, that's true. Yeah, the Austin timeline daylights. I mean, but the youngest, I guess, cuts through all of that daylighting at
The
the
youngest
Escondido.
daylights at around 60, 65, end of Cretaceous.
Yeah, which is your Escondido timeline, stratigraphically along the Balcones. Okay. And you're saying that the muds associated, that's interesting. So the muds predate the
magmatism.
And that's also happening at Denibakea?
Yep.
How do you pronounce that again? Because I always say it wrong. Denibakea is...
You actually got it right.
Is it? I thought it was Denibakea. Okay. In northeast Arizona, what mud volcanism evidence do you have up there? I haven't heard the mud volcanism story up around the Manets.
That's because you're not paying attention. You don't listen to the literature. But the literature doesn't get it either. They're dumb. and I'm an asshole.
Good to meet you, Stan.
I should turn around. Anyway, the reason they know that they call them sums, and they're just, I'd say in the last several years they figured out that there's two fundamental, and they still haven't. They're still trying to connect them. What's the sums, which is an acronym that stands for serpentine ultramafic breccia. And then the other diapirs, which are the ones that everybody takes pictures of, like Agathla Peak and Shiprock, New Mexico. And those are Minette diapir diatremes and dikes, but they do get, both of them actually have volcanism. But we spent some time obviously crawling around on Buell Park, and that's clearly a low temperature mud volcano conduit. And in fact, at Garnet Ridge and probably Red Mountain on the border of Utah and Arizona, they've actually erupted as flows. But Buell Park is a little bit deeper. But it's the biggest one.
The Minettes erupted as flows?
Yeah, they did, and so did these sums at Garnet Ridge and Red Mesa.
So at Buell Park, you're running around kind of the inside the crater kind of looking thing.
That's correct. Yeah, it's intruded into the Permian, the Cutler Group, whereas the things actually punched through the Cretaceous and the Jurassic, so they actually intruded a lot higher. That's, for example, at Garnet Ridge.
Wow. That's weird to think about. So the mud volcanism part is coming out and stratigraphically.
But that's what they are, is it's mud volcanism.
Uh-oh.
And the problem is that idiot literature has tried to connect the two petrologically. They've tried to say the Minettes are a fractionate of this ultramafic, really depleted K-pore stuff. Somehow it managed to fractionate a low silica, high K thing, which is ridiculous. They're fundamentally different types. And one is really hot.
Back to the mud volcanism thing real quick. You're saying the mud volcanism component of Buell Park is stratigraphically interfingering with older Permian age sediments where the Minettes actually...
That's correct. It's punching through it. The Minettes at Buell Park, which are present, intrude only within the diatreme area as a circular dike and as a differentiated intrusive.
Which is Cretaceous in age?
No, they've been dated. They're 25 million.
Oh, yeah. This is like not Oligocene, but it's Cenozoic.
It's Oligomycene.
So the mud volcanism that predates the Minettes at Buell Park, the mud volcanisms figuring out...
It's about 8 million years older.
The muds?
Yeah.
They're like 32 million and the Minettes are 25.
Yeah.
Wow. And stratigraphically, these muds are going out interfingering with Permian age rocks where the Minettes are coming all the way to surface and just daylighting as like dikes.
Yeah, but the Minettes also sill out locally into the Permian too. And that's where the reservoir is at Dinabatea.
Wow. And the muds at Dinabatea don't have any hydrocarbon story in them?
We analyzed for hydrocarbon. We didn't see a lot.
Wow.
However, the lithium systematically increases with where you are in the paragenetic sequence. So it goes from about 2 ppm up to about 45 ppm.
Biopark and
Correct. And
the
Green Knobs, which is immediately to the east.
yeah,
That's another subdiatreme.
those things punched up, connected to the
Yeah.
same deeper source.
Well, the stuff at Green Knobs comes up into the Jurassic,
Oh wow! So that just
but it
doesn't have the
doesn't
old.
daylight. It doesn't daylight either. But the overbet on the Defiance Uplift, which is where Beale Park is, that comes up into the axis of the Defiance monocline.
Wow!
That's in the Permian.
What the hell? That's not that far apart.
No, it's about, although you cross the main limb of the Defiance monocline, and then just as you get into the bend into the lower monocline, that's where you see that's why you jumped up section also. That's where you see Green Knobs. Anyway,
Fascinating that we went down that huge rabbit hole because of the thickness structure map of the Eagleford, which you're saying is this predated mud volcanism story to the big Balcones igneous province thing.
yeah, but it's using the whole Balcones fault system. So both species utilize the same conduits.
So where does that end? What the heck is going on there? So the mud volcanisms predating the igneous
So
mafic
the deep
story.
blue areas are highs. Those would be mud volcano highs, not basin lows. See
As
that
in,
you got to tell all those guys up at Austin that they have to flip their brains, and they'll
yeah,
immediately
well, help
lap
flip
you
my
up around.
brain. Help flip my brain for a second because the blue in this thickness map is based on, presumably, anyway, based
Pigment
on,
Eagleford thickness.
right, a top of Eagleford and a base of Eagleford, which is a black chemical mud deposit.
Right.
And these logs are going to have where it's really thick and then it thins out into some other carbonate or a sand or something else.
Yeah,
The
like it
Eagleford,
does at the golf course
and you're
where it goes
saying that
to San Marcos High.
where the Eagleford right now is showing thickness, you're seeing it as that's the center point of a mud diapir.
You got it.
What is going on in the southwest corner of this thing? Do you think that's just lack of data and it's just overly
No, it's
projected?
overall thickening towards the Gulf of Mexico.
That's thickening towards Mexico, not the Gulf of Mexico. I mean, it's
Well, no,
because
I mean it's southeast thickening.
that's
Yeah.
to me that this map is southwest
All right.
thickening.
You could say Mexico. I'll give you that.
And so what the hell's going on there? Is that a massive true mud volcanism, like massive mud
No, I think
volcanism?
you're mixing that with other sedimentology. I would just stick to that one trend that goes up the Balcones.
Like your confidence in this map is more up here than it is down in here.
Yeah, and that's where all the drilling is.
Well, yeah, I mean, that's where you have your thickest, what would be considered the unconventional target. So, of course, you're going to land in the thickest part of it, and you're going to find these zones that have hydrogenated the kerogen enough to be commercial oil and gas.
That's right.
You get off that stuff, you get into the greens or the oranges, you're just, not that there couldn't be a zone there that's been hydrogenated very well and efficiently, but your whole window
Well,
is
that's
shrinking.
our golf course story.